So dear students, parents and colleagues, good afternoon. My name is Angela Luca and I'm Kültür2000 College International Baccalaureate Diploma Program Coordinator. I'm very pleased to welcome you today to the fourth Kültür Nobel Talks live streaming. In times of social distancing, lockdowns and travel restrictions, it is our desire as educators to tailor unique learning experiences for our students and to encourage them to keep learning and searching for knowledge. In line with these principles, today we are honored by the presence of Professor Martin Karplus, an Austrian-born American theoretical chemist and a Nobel laureate. Good afternoon, sir, and welcome to Nobel Talks live streaming. How do you do?
Thank you. How do you do? And I'm very pleased to be able to have this opportunity to do this. It's really something in these uncertain times that I can do, and if it's helpful to your students, I'm very pleased and in a way honored to have been chosen to participate
Thank you, sir.
in this program.
Thank you very much, sir. I'd like to add a few details, if you don't mind, about your prize motivation for our students, for the younger ones. Professor Karplus was awarded the 2013 Nobel Prize for Chemistry for developing accurate computer models of chemical reactions that were able to use features of both classical physics and quantum mechanics. Sir, during your Nobel lecture at Stockholm University, paraphrasing the American philosopher Ralph Emerson, you stated that you've gone where there was no path and left a trail. If I may ask, what made you decide to become a scientist and dedicate your life to research?
Well, I always was very much interested in the world around me. And when I was young, my family felt that in each generation we had a medical doctor. And so nobody else had any interest in being a doctor. But I used to go around when I was little and bandage chairs and such. But when I came to be a student at Harvard University, I realized that rather than becoming a doctor and treating people, I was more interested in actually trying to find out what was going on in living systems. And it was basically with that idea in mind that I shifted from medical school to getting a PhD, actually with Linus Pauling at Caltech, which prepared me for my career. And one thing that I realized at that time, which was very early, is that to understand living systems, you didn't only have to study biology, but you also needed to know chemistry and physics. And that's the program I followed as an undergraduate at Harvard University.
I see. Thank you very much. I have a little curiosity. As I said, I teach epistemology. So my question is, how does creativity play a role in science? Because our students think that creativity is not very important in science. They think that creativity is important only for arts, for different kinds of arts, and maybe, what do you think it plays as a role in science, creativity?
Well, I think it's an essential part of doing original work in science. That's basically the originality is another face, if you like, of creativity. Now, another aspect in my own life is that, and it's true of many other outstanding scientists, that they don't have in their life not only the science that they're doing, but that they're interested in many other areas. And in my own case, I'm not only a Nobel Prize winning scientist, but also a well-known photographer who has had exhibitions all over the world. And the third is that I'm a well-known chef and have worked in many of the most famous three-star restaurants all over
That's
Europe.
interesting. That's
so
interesting.
It's really this mixture that I think makes you able to do outstanding work in other areas as complemented by these various areas. So that's my story. I'm not sure it's the same for everybody else, but I know many Nobel Prize winners are musicians, which I'm not. And so they each have sort of another string to their bow, as the expression goes.
Okay, thank you for your reply. Kültür and Kültür2000 College students, they made some research and they have prepared some interesting questions about your discovery, and they would appreciate the opportunity to listen to your answers. We're going to listen to their questions one by one. We start with question number 1, prepared by our student, Eyüp.
Hi, my name is Eyüp Ginger. I'm ninth grade at Kültür Koleji Science High School. How did you feel after getting the Nobel Prize, and what helped you on this path to be success? Thank you for your time.
Well, I guess I was surprised to receive the Nobel Prize. The work which was involved in the Nobel Prize was done in the 1970s. And although I, wondered over the years, many people said, yeah, it's worth the Nobel Prize. But I had sort of decided that somehow the world has passed me by. And, in the Nobel Prize, you're supposed to be rewarding something that was done recently.
Yeah.
But 2013 and 1970 can't be regarded as recent. So I've sort of just given up. But then, of course, when it actually happened, what happened is that we were in the U.S., so it was 5:30 in the morning. My wife and I were asleep. She was closer to the telephone. And she said, somebody wants to talk to you. And so I said, okay, pass it to me. And so several people said, they wanted to congratulate me in winning the Nobel Prize. And I thought it was just a joke. That had happened before. But finally, the last person who was the secretary of the committee and was a biophysicist who I knew, so she said I'd won the Nobel Prize. So then I actually believed this. And basically, that was the other part of the question. I'm just looking it up.
And what helped you on this path to success?
Well, yes. The main thing was, I think, faith in myself in some sense. Not that you have faith that everything you do is correct, but it very often happens as you work. And I can mention what happened when we actually started these simulations in the 1960s. That was before we were working on biomolecules. And so I had this idea of trying to apply methods to, protein molecules similar to ones that were tried for simple molecules. And when I mentioned this to my colleagues in chemistry, they said, well, we can't really understand a very simple molecule in detail. So how can you imagine that you can do something on big molecules like proteins? And the biologists said, well, if you could do it, we wouldn't really care about what you're doing. So given these very negative responses, I still went ahead and did it. And of course, now the situation has changed and everything is fine.
Okay, thank you for your reply. We're now ready to listen to question number 2, prepared by our student, Sude Nur.
Hi, my name is Sude Nur Yildirim. I'm in 11th grade in Kültür Science High School. So my question for you is, has your study, multiscale modeling for chemical systems, ever been used in biochemistry, especially in pharmaceutical industry? If it has, what kind of awareness has it created? Thank you for your attention.
Yes, the answer is it certainly has been used in applications, which I suppose is in fact one of the basic ideas of Nobel himself, that it's what you do should it be for the benefit of mankind. And so we developed a program which is called CHARM for chemistry at Harvard Molecular Mechanics. And this program, which we developed for our own research, but is now very widespread in the pharmaceutical industry, where people are using it, as we have done in some problems that we were interested in, to design inhibitors for proteins that are causing certain diseases. And so by designing a small molecule that will bind to them, you can make them inactive, and in that way actually either make a disease more mild or cure it. And of course, right now, with the coronavirus, this is one of the areas where people are trying to make better molecules at this time, and they in fact use our techniques. It turns out that one of the molecules that's most likely to be used recently is the remdesivir, which was created by Gilead, and the person actually who has been the vice president in charge of doing these computer modeling is actually a former student of mine.
Okay.
So that sort of really indicates, what has happened over many years, but even in this on the coronavirus pandemic, the same type of methodology is still very useful.
Thank you very much, sir. We're ready now to listen to question number 3.
Hi, my name is Mehmet Özdemir. I'm a 90th student of Kültür Koleji. Today, I'm going to ask you a question about your new research. Explain what is required to be able to meaningful simulations of proteins, as well as of other systems, including those of interest in organic and inorganic chemistry. Thank you for your reply.
Well, if I understand the question, the first part of it is, what do you need to be able to do the type of work that you do to do molecular simulations? The most important thing is to know the interactions between the different atoms of which the protein, let's say, but it could be a nucleic acid. I mean, it doesn't have to specifically be a protein. You have to know what the forces are between the atoms. And for that, you have to do basic calculations to determine them. Once you know the forces, you know that you can integrate Newton's equations to get the motion as a function of time. And the other aspect is that you have to have enough computer time. And the computers have always been a limitation. As the computers get bigger, our ambitions get bigger, and we try to do bigger systems. But you have to be able to do a large enough number of simulations to get statistically meaningful results. Because if you just do one of them, it may just be an accident what happens. And so you have to do maybe 10. Though even doing 2 is much better than doing 1 to get results that are statistically meaningful. And exactly this, you asked, I think the second part was, can it be used anywhere else? And it turns out, the problems of using it anywhere else in chemistry, and it's being widely used in organic and inorganic chemistry, And it's basically just the same problem. You have to find out what the interactions are. And once you know them, you do just exactly the same type of calculation. And there people are, I mean, one thing that a number of my colleagues in Strasbourg, where I spent half of my time, have been working on is making compounds, organic cage compounds that will, say, bind a sodium ion and be able to eliminate it from the system. And in fact, one of them actually got a Nobel Prize recently for this type of work. So,
yes. Thank you for your reply. We have now question number 4, prepared by our student Çınar.
Hello, this is Çınar Özmer from Kültür Koleji 9A. Professor, I have a question for you. Your study was crucial in comprehending and modeling how computers can be used efficiently in chemistry and biology. For instance, to learn how proteins and enzymes regulate chemical reactions in living things. Could you briefly explain how you achieved this? Thank you.
For your question, okay, let me think about it a little bit. Well, if one wants to know how an enzyme works, you have to compare the rate. Well, first of all, you have to compare the rate of a reaction in an enzyme relative to that rate in solution. An effective enzyme will increase the rate. And so we have to say, well, what determines the rate of a reaction? And there's what's called the Arrhenius Equation. Actually, Arrhenius got a Nobel Prize. I think it was in 1903 or something. He's Swedish, and the Swedes tended to give Nobel Prize to their colleagues in the early days. And the Arrhenius Equation says that the rate of the reaction is equal to some factor times an exponential minus delta E over KT, where delta E is the activation energy, the energy that's required for the reaction to occur. And since it's in an exponential, if you can change that delta E, you can affect the rate of the reaction. And basically what enzymes do is reduce delta E. And the methods we developed can, first of all, calculate this difference in energy between the initial state and the barrier over which the reaction has to go the barrier height. And with that, you can find, if you compare the barrier height in the enzyme with the barrier height in solution, how much the enzyme increases the rate of the reaction. Now, in addition, you can also, in fact, use molecular dynamics to just calculate the rate of the reaction using these results and get not only a mechanistic picture, but actually the details that the reaction follows. The trajectory is what says that the reaction follows as it takes place. Does that answer the question?
Yes, thank you very much, sir. We're ready now to listen to question number 5, prepared by our student, Cemre.
Hi, I'm Cemre Ismail and I'm a 10th grader at the Kültür 2000 Science High School. And I would like to ask you a question about your research. It is incredible that your research was done in 1960s when computer memory was limited to a certain number of words. Could you please tell us about the difficulties you encountered and the solutions you produced during your research? Thank you.
Well, that reminds me of long ago, and where I was at the University of Illinois, and the University of Illinois had a big computer, as it was called in those days, which, as a student mentioned, had only 1,000 words of memory. And it turned out, in fact, that in those days, in fact, at that time, I did developed an equation which is now called the Karplus equation, which probably any student in organic chemistry knows about who doesn't know anything else about my work on proteins, because it's very widely used. And basically, it is used to determine the energy of a system. And I don't know whether you can, yes, you can see my hands. That
yes.
If you have two hydrogen atoms here, and then there's a carbon atom here, and a carbon atom here, and another hydrogen atom, this equation tells you how the energy changes as you rotate around this single bond. And that it turns out to be extremely useful in determining, getting information about the structure and function of molecules. Now, when I did the research, it turns out that to actually calculate this by valence bond theory, which I learned from Linus Pauling when I did my degree, it's relatively easy to do it in one of these calculating machines that we had at this time. But if you want to calculate it, for many different angles, then to do that on a calculating machine gets to be rather, time-consuming, and more important, in each calculation you do, you have to be sure that you haven't made a mistake. However, if you make a computer program which calculates this and check it for one angle, then it's very easy, to put in each other angle and get the values. And so having this computer program is was important for that reason when I did the calculation. Also turned out that just after I'd done the calculation, before it was published, there were some experiments that were done which could be interpreted by this. Now, getting back to the computer, it was interesting machines, one might say. The way you don't use cards, or now you do it all automatically, but you used paper tape. There were very thin strips of paper, and you wrote your program by putting in dots in various places that the computer could interpret. Now, sometimes when you put in these dots, you made mistakes. And so what you
have to redo it again.
Yeah, what we used was nail polish to fill in the dots and correct the tape. And it worked fine. And so that's the story of how we did it on this simple little computer.
Okay, double functional polish nail. Okay, that's nice. Okay, great. And we now have question number 6, prepared by our student Aslı.
Hello, my name is Aslı Soyhun. I'm an IB student in Kültür2000 Anatolian High School. As an international baccalaureate student, we learn how important both theoretical knowledge and experimental methods are, especially in our science classes. When I read about some of your research, I noticed that you have shown how parallel these two can be with each in modeling, with molecular dynamic simulations. In what other branches of sciences can we use this type of modeling to explain them? Thank you.
So, fun question. And maybe it can be used in many different areas, but in particular, one area that's perhaps the most extreme is to use it in studying the dynamics of stars in galaxies. Now, the interesting thing is, while in doing chemical problems, as I've mentioned earlier, you have very complicated interactions that you have to use. As far as stars are concerned, the interaction is very simple. It's just the Coulomb force 1/r. And so, in principle, doing the calculation, of course, the time scale that you use is instead of sub-nanosecond, which is the time scale for the motion of atoms, or picoseconds even. For the galaxies, it's in light years. So the calculations, and use very large time steps compared to the smaller ones that we use for atoms and molecules. The other point is that because the motions, go over light years, there are relativistic corrections for them. And so, but in principle, that's basically, about as far out as I can think that one might include this type of calculation. Those are much more closer problems at home, but I thought it would be fun to mention this one.
Thank you, sir. Thank you for your reply. Professor Karplus, in the name of Istanbul Kültür Educational Institutions, I sincerely thank you for joining us at Kültür Nobel Talks live streaming. It was an honor to have you in attendance today. I would also like to thank our students. I hope that you found this event both informative and interesting. Thank you again, sir, for joining us today.
Well, thank you for giving me the opportunity. I've always wanted to visit Istanbul.
Okay, you're welcome.
It's very exciting.
That would be great for us to have you. That would be great for us to have you and visit our school. That would be great.
I mean,
please let us know.
In these days where Istanbul and the whole country is not that stable, is it something safe to be able to do, or what do you feel?
Yes, of course it is. We're very safe here. Yes, of course we have the same lockdowns, the restrictions every other country has in Europe, but they evacuated very, very early, and results are very positive. Yes, Turkey has acted really fast, and they have very strict rules, and we are respecting them, and results are really better than other countries in Europe. I can say that.
Yeah. Well, maybe when things return to normal,
yes,
new normal, I don't know how it'll be. Maybe
a couple of months, I think everything is going to be all right.
Yeah, maybe I'll have a chance to really visit there.
Yes, that would be great for us if you could come, and join us and visit our school. That would be so. I can't imagine for our students. What an honor. Thank you, sir.
Yeah. Well, thank you for making this possible for me, and I've really enjoyed meeting you and meeting the students.
You enjoyed.
I think it was a great opportunity.
Thank you very much, sir. Again, thank you.
Thank you. Great. Thank you. And goodbye to all the students, and thank them for their questions.
They are listening to us. Thank you very much.
Guess we get it up. Okay, well, say goodbye. Yeah.
Goodbye.